Hi Mom, welcome back to Learning Physics with me. So far we've learned a lot of cool things like mass and acceleration equals force. We've also learned vectors, velocities, and energies. But everything that we've studied so far, all the objects have been moving in one dimension. And what I mean by one dimension is every object that we've studied has been moving only in the x direction or only in the y direction. Like last week when I was doing the squat, the weights were only moving in the y direction, up and down. But what happens if an object is moving in the x direction at the same time it's moving in the y direction? It's pretty simple. All we have to do is calculate the force in the y direction and then calculate the force in the x direction. This is because the vectors are acting independent of each other. This just means that when we're performing the calculations for the force in the x direction, we're not using any of the y variables from the video. And vice versa, when we're performing the calculations for the y direction, there are no x variables going into that formula. To help you understand this week we'll be throwing a tennis ball through the air. Now it's going to take a curved path through the air, so it's going in the y direction at the same time it's moving in the x direction. We'll calculate the forces independently of each other. That's the y force and the x force. Once we have figured out the forces and maybe a drag coefficient that we learned a few weeks ago, we'll plug all those numbers into the code and hopefully the model will accurately depict what we saw in the real time. Now let's go outside and throw this tennis ball. Here's the video of us tossing the tennis ball. Now one thing to note is our calculations will be, in the x direction, will be negative since we're tossing the ball from right to left. The graph being shown right now is the x position versus time. And we'll talk a little bit more about these graphs here in a second. Before we actually go and look at the graphs that Tracker made, let's think about what they should look like. What about the x versus time? We've already kind of seen it. Let's see if it makes sense. So the video starts from the right and goes to the left. So the right side is the positive side, so it starts obviously at its highest x value. Now as time goes on, it's constantly moving to the left, so it's constantly moving downwards. So that linear graph actually does make sense. What do you think the y position versus time should look like? Well, it starts at its lowest point, and as the ball gets tossed upwards, as time goes on, it reaches its highest point, and once it gets to its highest point, it then starts to fall until the partner catches the ball and it's back to its lowest y position. Now to the really cool graphs, the velocity graphs. What do you think the x velocity versus time should look like? There's no real forces except for maybe a little bit of drag acting on the x velocity. So that should mean the x velocity should remain mostly constant. So if it starts somewhere in between 1 and 2 meters per second, it should stay just like that with maybe a little decline due to a little bit of drag force. What about the y velocity? The y velocity, if there is drag, will have drag, and it will also have that mass times gravity force acting on it. So what should it look like? It'll start at its maximum point, and then those forces acting on it as time ticks away will constantly make it slow down. Now let's see if the graphs that we theorized match up with the graphs from the real world data. Here we have x position versus time, y position versus time, x velocity versus time, and finally y velocity versus time. So our predictions were correct. The graphs that we drew on the whiteboard, the ones that we theoretically came up with, and the ones that we thought that the graphs should look like, actually did look like the graphs that Tracker spat out. Now we can take some of the data from the video and we can plug it into the computer code. And the computer code will use that data to update the velocity and the position of the ball that it's created. And we'll compare what the computer code came up with, because the computer code is purely calculating physics. And we'll compare that to what actually happened in the real world. We'll compare the computer code's highest y point to the highest y point that we videoed. And they should end up being really, really close together. Now, before we look at the computer code, let's talk a little bit about the forces. So at the very beginning of the video, I brought up forces and I said that they work independent of each other. Next week, we'll get more into the calculations of them when we roll a cart down a ramp at a certain angle. But this week, I just want to get the point across that the forces do act independent of one another. That's the forces in the y direction act independent of the forces in the x direction. If you remember the graphs, the x velocity was a horizontal straight line. It was neither speeding up nor slowing down. But if you look at the velocity in the y direction, it started at a high velocity and ended at a low velocity. That's because there was a force in the y direction. It was gravity. And this is how we would write it. The force of the weight was 0 in the x. There was no forces acting on the tennis ball in the x direction. And it was negative mass times gravity in the y position. And it's negative because the gravity is pulling downwards in the y direction. Since we've already seen the code a couple of times, I'm only going to show you the things that are different. Like this week, it's very important to notice that the weight is in the y direction only. See where it says weight, it's negative mass times gravity, like we said, but then it's in the vector and it says 0, 1, 0. It's that middle one that's showing that it's happening in the y component only. Other than that, everything else is pretty much the same. The drag is so negligible, I didn't count it. Force is the weight plus the drag, so it's just the weight. And velocity is velocity being updated by the acceleration, that force divided by mass. And the time is being updated by that delta t, which is 0.01 seconds. Oh yeah, and the velocity that's being updated is up here at the top, where it's negative 1.8 and 3.335. Those are the x and y initial velocities, and where it says velocity in the while loop, that's where it's being updated by the acceleration. So how did we do? Well, if you look to the right on the graph that the computer code came up with, you could see the y curve position. If you look at the very peak of that curve, it was 1 meter high. That's how the maximum point that the ball traveled in the computer code. Now, if we go back to the real world video that we shot and you look at the graph that Tracker made from that video, you'll see that the peak of the y position of the ball was 1.1 meters. So before we even do a percent difference, we can tell that it was extremely close. So if you take the 1.1 of the graph minus the 1.1 of the computer code graph, divide it by the average and multiply it by 100, you get 9.5% difference. And remember, anything under 10% we can work with. So that's all I have for you this week. Next week, like I said, we'll talk more about the forces in the x and y direction. But this week, I hope you learned something. Thank you for watching.